Hello and welcome to the presentation of probably one of the shortest papers at Stock this year. Our paper is 4 pages long, and the goal of this talk is therefore to give an almost complete proof of our result. This is going to be about the K-server problem, and it's joint work with Marcin Bienkowski, Jarek Bürker, and Lukas Schiess. And I am Christian Köster. So the K-server problem is defined as follows. We have a metric space, and we have K servers, in this example, three servers and located in this metric space. And now points of this metric space are requested one by one. So when a point is requested, then the algorithm has to decide which of the 3 servers should move to that point. And after the server has then moved to the point, the next point will be requested. And again, the algorithm has to select one of the servers to move there, and so on. And the goal of the algorithm is to minimize the total distance traveled. So the cost is the total distance traveled by all servers. And as usual in the area of online algorithms, the performance of such an algorithm is measured by the competitive ratio. So that's the worst case ratio between the cost of the online algorithm, which does not know the future requests, and the cost of an offline algorithm that could compute the optimal solution, knowing all the future requests. Let's briefly revisit the state of the art for this problem. So for deterministic algorithms, it is known that the competitive ratio is roughly k. So a lower bound of k was shown by Manas and others when they first introduced this problem. And 6 years later, Koutsoupias and Papadimitriou then showed an upper bound also of 2k minus 1. So this is matching this lower bound up to a factor of 2. And the famous K-server conjecture states that actually the competitive ratio should be k, precisely k on every metric space. For randomized algorithms, there has been a lot of recent progress. So there's also an analog randomized K-server conjecture, which states that the competitive ratio of randomized algorithms ought to be log k, or up to a constant. And so it was shown recently by Bubeck, Cohen, Lili, and Madri that the competitive ratio on any endpoint metric space is at most log square k times log n. And there was also another paper by Lee based on this, which proposed a technique to get a competitive ratio for any metric space that's polylogarithmic in only k and not depending on the number of points of the metric space. In terms of lower bounds, there's a lower bound of order log k for some metric spaces. So this would be matching what is conjectured for any metric space. And also for every metric space of at least k plus 1 points, it is known that the competitive ratio cannot be better than log k over log k. So almost the same lower bound, actually. Right, so one thing one should take away from this previous slide is that the competitive ratio as a function of k goes to infinity as k goes to infinity. And this is one of the reasons that motivates the HK server problem. So it's basically the same problem, except that we changed the definition of competitive ratio. So this is it's also called the K-server problem against weak adversaries. It's the resource augmentation version of the K-server problem. So the only difference here is that the offline algorithm that we compare ourselves with now doesn't have K servers, but it has H servers, where H is some number smaller than K. So this weakens the offline algorithm and therefore should allow us to obtain a better competitive ratio intuitively. So we say the algorithm is row competitive now if the cost of the online algorithm is at most row times the cost of an offline algorithm, where the online algorithm has K servers and the offline algorithm has H servers. And okay, we also allow some additive constant here. And we then use the notation Rxhk for the infimo of all of such row on some metric space X. So Rxhk is basically the competitive ratio of the HK server problem on metric space X. And okay, one could define this for deterministic and randomized algorithms separately. It's going to be a different number. Let's just think of randomized for the purposes of this talk, but it doesn't really matter that much for today. What is known here, well, what was shown very early in 1985 by Slater and Darjan, is that when X is the uniform metric, in which case the K-server problem is equivalent to the paging problem, then you can choose k just an arbitrarily small factor larger than 1, and then, well, k as an arbitrarily small factor larger than h, and this will then lead to the competitive ratio dropping from k or h to a constant. And okay, this constant of course depends on epsilon, but it does not depend on k and h anymore. So the competitive ratio drops from k to a constant by only slightly increasing the number of online servers. And this really shows the power of this resource augmentation setting, of course. So the main question motivated by this is this true for every metric space? So is it true for every metric space X that if k is just an arbitrarily small factor larger than h, that the competitive ratio will drop to a constant? Or one can ask a weaker question, is it true at least when k over h goes to infinity that the competitive ratio becomes a constant? So this is the question that we're going to be concerned with today. So let's see what else is known about this. Well, there are some cases when we have a positive answer for both of these questions. So on uniform metrics, as I just mentioned, and then also this result was generalized to weighted star metrics and eventually to bounded depth trees, that in all of these cases, you can get a constant competitive ratio when k is just an arbitrarily small factor larger than h. And the references here are for the results when they were shown for deterministic algorithms. For randomized ones, you can get a beta quantity RHK, and yeah, there are also results for all of these cases. For general metrics, however, nothing is really known about how to use these extra servers. So the best strategy we have on general metrics, when we have k servers and the offline algorithm has h servers, is to simply not use the k minus h extra servers we have, and then just run some standard algorithm on the h servers. So we don't know how to make use of these extra servers that we have in general. However, there are also no real lower bounds that are known. There are only constant lower bounds. So there was first shown a lower bound of 2, which holds even when h is 2 on the line metrics for any k. And this was then improved to 2.4 and 3.1. So even when k over h goes to infinity, this competitive ratio will not be less than 3.1. But yeah, you can see the gap here is still between a constant, 3.1, and the upper bound being h or 2h minus 1 in the deterministic case, induced by simply not using the extra servers. Okay, so just to remind ourselves again, these are the two main questions we therefore want to address. And our main contribution in the paper is to answer these questions, and the answer, which might be surprising to many, is that, well, the answer is no. So more precisely, we show that there exists a metric space X such that the competitive ratio of the HK server problem on this metric space is at least of order log h. So this is true for any k. K can be arbitrarily large. So in particular, it is not a constant. And yeah, let's see how one can prove this. So the key ingredient is the following lemma. So let rho and d be some arbitrary numbers, and then define some other numbers, and you don't have to pass these definitions yet. The point is, there exists a metric space, or a tree, TD, which will be of depth d, such that the competitive ratio of the HD-KD server problem on this metric space is at least rho. And yeah, you can see we chose rho arbitrarily. So we can make rho arbitrarily large, and then we can make d arbitrarily large so that this d over 2g is bigger than epsilon. And then this lemma will already imply that the answer to the first question is no. And we will first prove this lemma, and then we will also see how we can use this to answer no to the second question and get this lower bound of log h. So the proof works as follows, and I have a little asterisk here, which I will explain later. So we need to construct this metric space TD, this tree, So it looks as follows. We have a root, and the root has infinitely many children. And at each child of the root, there is a subtree of type td minus 1. And so td minus 1 is just the subtree induced by the induction hypothesis, or when d is 1, then td minus 1 is just a single point. And now the number of offline servers, hd, we will think of it as there being g groups of offline servers. So each group is supposed to have size hd minus 1, and therefore the number of groups is hd over hd minus 1, which is g by definition of hd. And the offline algorithm will always keep an entire group together in a subtree. So when some offline server moves to a different subtree, then the entire group of offline servers will move to that subtree. And we can also think of the online servers as being in groups. And in that case, the number of groups, if the groups of online servers have size kd minus 1, then the number of online groups would be kd over kd minus 1. And you can do a little calculation to see that this is at most g plus 1/2. So for the online algorithm, we cannot control, of course, that the online algorithm keeps its servers in these groups, but it will still be useful to think of the number of online servers as being in groups. And okay, what I did not say is that this proof is going to work for both deterministic and randomized algorithms. And in the case of randomized algorithms, when I say there are X many servers in a particular subtree, what I mean is that the expected number of servers is X in the subtree. And of course, the expected number of servers is a deterministic quantity. So we can basically think of the algorithm as being deterministic. And the idea of the proof is going to be that we want to achieve the competitive ratio rho in these subtrees at the bottom. And we also want to achieve competitive ratio rho in terms of cost that's incurred along the edges adjacent to the root. So the request sequence works as follows. We first select some subtree that doesn't have any online server mass. And then one complete group of offline servers of size hd minus 1 goes there from one of these other subtrees. And okay, now I took the offline group from this subtree, but actually we will, well, we don't decide yet from which subtree we take the offline group. So I make this now light blue to just remind ourselves that in fact there are not 5 groups, but only 4 groups here. So one of them is actually missing because it already moved to the right. We will decide later which one. And now we're going to issue the request sequence from the induction hypothesis in this subtree that we just selected. And we do this until the number of online servers here has grown to kd minus 1. And once this happens, we look which of these subtrees on the left does now have the lowest number of online servers, or expected number of online servers, which would be this one. And then we say, okay, this is not a subtree from which we took the offline group that went to the right. So we do keep the offline group here. So I changed the shade of blue here. And now we're going to issue the request sequence from the induction hypothesis also in this subtree. Again, until the number of online servers has grown to kd minus 1, which of course, again, will reduce the number of online servers in the other subtrees. It could also reduce the number of online servers in this last subtree. If this happens, then we just continue the request sequence in this last subtree until eventually in both of these subtrees, the number of online servers will be kd minus 1. And then we just continue like this. So again, we pick the online subtree with the subtree with the smallest number of online servers, which would be this one. And we issue the request sequence from the induction hypothesis to increase the number of online servers. And we do the same then here and here as well. So at this point, we decide that the subtree from which we have taken this group that went to the right is the first one, because that's the one in which we never issued any requests. And yeah, we can see immediately that within all of these subtrees at the bottom, we have competitive ratio rho simply by induction hypothesis. So what remains to show, and yeah, also in the right? In the base of induction, there's simply no cost within the bottom because they are just single vertices. So what we still need to show is that at the top, we also have a competitive ratio of at least rho in terms of the cost that's incurred at the top edges. So that's the goal. Okay, here's just a typical situation in the middle of such a phase. Okay, how do we show this? Well, so consider some situation when J groups are fixed. So by fixed, I mean that we have played in these subtrees already, and yeah, we have therefore decided that there is an offline group in one of these J groups. Then, and yeah, there are KD minus 1 online servers in all of these groups. This means that because there are at most G plus 1/2 online groups, therefore in the other subtrees, there are G plus 1/2 minus J online groups left at most. And there are G plus 1 minus J candidates for the subtree that we will play next, because there are G plus 1 such subtrees in total, and we have already fixed J. So therefore, in these candidate subtrees, the average number of online groups is at most G plus 1/2 minus J over G plus 1 minus J. And we can rewrite this as 1 minus 1/2 times 1 over G plus 1 minus J. So this fraction of a group will be in the average candidate subtree, and therefore at most this much will be in the minimal candidate subtree, where the number of online servers is minimal. And that's the one where we'll next issue requests. So this means that when we issue requests in this subtree, then 1/2 times 1 over J plus 1 minus J fraction of an online group must switch to that subtree. So such a fraction of a group must travel along the top edges. And if we then sum this up over all J, then we see that the number of groups that are switching along the top edges is therefore at least of order log G. And now we had chosen G exponential in rho, and therefore log G is at least rho. So this shows that at the top, we also have this lower bound of rho, and we saw that we also have it at the bottom. So overall, we have a lower bound of rho on the competitive ratio. And yeah, so let me reveal why I had this asterisk. Well, the reason is that we have to be a bit careful here when phases are incomplete. And what this requires, to make this work also when phases are incomplete, we just need to choose these edges at the top much longer than the edges, much longer than the edges below. And yeah, that can be made to work. And yeah, that is basically the proof of this lemma. So let's now look at how we get log h from this and how we then also answer the second question negatively. So recall just the definitions from the lemma before. And now we want a single metric space, which looks as follows. We have a tree again, and the root has infinitely many children of type T1 and infinitely many of type T2 and TD and so on, where TD are these subtrees from the lemma that we've just seen. And well, actually TD does not only depend on D, but also on rho. And we're going to choose rho here so that D equals rho times G. And then say that all the servers start at the root. So we have some relatively small number HD of offline servers and a much bigger number of online servers, K. And the request sequence just uses the lemma basically. So in this case, if H is the number of offline servers, we will just play in this, well, we will only play in these subtrees TD. So we select one, we move the offline group there, and then we issue the request sequence from the induction hypothesis in the subtree until we have KD online servers there. Once this is the case, we move our offline group to a different subtree. We will abandon this previous subtree forever. And now we do the same in this subtree. So again, we issue the request sequence until the number of online servers has grown to KD. And we go to the next subtree and we do the same again, and so on. And it doesn't really matter where the online servers come from, whether they come from some previous subtree or whether they come from the root. The only thing that does matter here is that each time we select a new subtree, there must be KD online servers that travel along this top edge. And there are only HD offline servers that travel along this edge. So therefore, the cost ratio between online cost and offline cost at the top is KD over HD, roughly. And this, we can see, is basically this 1 plus D over 2G, because we defined rho so that D is rho times G, we then see that this is of order rho. So we have a lower one of rho on the competitive ratio, what's incurred at the top. And because of the lemma, we also have this lower bound of rho at the bottom. So overall, the competitive ratio is at least rho. And now, yeah, we can just transform this. So rho, because of this equation here at the bottom and the equations at the top, can be seen to be at least of order log HD. And yeah, HD is just the the number of offline servers rounded down to some power of G. And yeah, so that's how you then see this log HD lower bound. And you see that it doesn't really matter how many online servers there were at the root. It was no advantage of having more because there still need to be traveling so many along this edge. So just to, yeah, so this is the theorem we just proved. There is a symmetric space where the competitive ratio is at least log H, so not a constant. And one corollary is that there exists no metric space where, well, no, there exists no algorithm that has a constant competitive ratio for the infinite server problem on general metrics. So the infinite server problem is the same as the K server problem, except that K is infinite. And we then require that all servers start at the same point to avoid trivial cases. So it was shown, well, we showed with Koutsoupias and Lazos before that the existence of a finitely competitive algorithm for this problem would be equivalent to a positive answer to the questions for the HK server problem. And now, because we have a negative answer, we therefore see that there cannot exist such an algorithm for the infinite server problem on general metrics. And we could also express this lower bound as a function of the depth D of a tree, and then it would be logarithmic in the depth. Okay, so let me conclude. We've seen the first super constant lower bound for the HK server problem, which implies that there exists no constant competitive algorithm for the infinite server problem. But there are still some significant gaps between the lower bounds we've shown and the bounds that we have in the classical non-augmented setting. So one question one could ask is, are weak adversaries actually weak? Or is it still possible to have an algorithm that uses extra servers and beats the quality of the algorithms that we have that don't use these extra servers? And yeah, so more precisely, the gap in the deterministic case is doubly exponential, and in the randomized case is singly exponential. So one question is, can we improve this lower bound for deterministic algorithms? So our construction is, well, it works for both deterministic and randomized algorithms. And yeah, one would usually expect that for deterministic algorithms, one should be able to prove a larger lower bound, but we haven't been able to do it. And one of the key takeaway messages maybe also is that, well, we were first trying to construct directly a lower bound for deterministic algorithms because it seemed it should be easier, but it turned out that yeah, this didn't. Well, we found it harder. So when we started thinking about randomized algorithms, then this actually helped us to find a lower bound because it changed our way of thinking. So a takeaway message is that it can be easier to prove a randomized lower bound than to prove a deterministic lower bound, even though, of course, proving the randomized lower bound will then also imply a deterministic algorithm, a deterministic lower bound. And yeah, that's it. Thank you for your attention, and goodbye.